What is the best way to size buffers for large DSP datasets? Imagine trying to listen to a long song or analyze a big chunk of audio without missing a beat. That's what buffer sizing is all about in digital signal processing. When working with large datasets, choosing the right buffer size can make or break your system's performance. So, how do you find that sweet spot? Let's break it down. First, remember that a buffer is like a temporary holding area for data before it gets processed. If the buffer is too small, your system might run out of data to process, causing glitches or delays. If it's too big, you risk increased latency and higher memory use, which can slow everything down. The goal is to balance these factors. Start by looking at the signal itself. If you're analyzing a periodic signal like a sine wave, the buffer should hold at least one full cycle of the wave. For example, if your signal has a frequency of 1000 Hz, the period is 1 millisecond. With a sampling rate of 10,000 samples per second, that means the buffer should contain at least 10 samples to cover one cycle. For better accuracy, you might want more. Next, consider the processing algorithm. Fast Fourier transform algorithms work best with buffer sizes that are powers of 2, like 1024 or 2040 examples. These sizes optimize computation speed and efficiency. If you're doing spectral analysis, larger buffers give you better frequency resolution, but they also increase processing time. Memory constraints are also key. Your hardware might only have a certain amount of available memory. Larger buffers take up more space, so you need to ensure your buffer size fits comfortably within your system's memory limits. For example, if your system has 2 gigabytes of RAM and your dataset is huge, you might want to keep buffers under a few megabytes to leave room for other processes. Many digital signal processing systems use circular buffers. These are like endless loops that keep data flowing smoothly without shifting data around in memory. Properly sizing these buffers involves setting the buffer length, the step size, and managing read and write pointers carefully. This setup helps prevent data loss and keeps processing seamless. Frame-based processing is common too. Instead of handling data sample by sample, you process chunks or frames. The size of these frames is your buffer size. Larger frames mean less frequent processing but more delay, while smaller frames process faster but requiring more CPU effort. Overlapping frames can improve accuracy, especially in spectral estimation, by analyzing overlapping chunks of data. Sometimes, buffer size can be predicted using formulas that relate to the data rate or bandwidth. For example, if your data stream varies in speed, you might need a larger buffer to handle bursts without losing data. Empirical testing is also essential. Running your system with real datasets helps you fine-tune the buffer size for optimal performance. In filtering applications, buffer size relates to the number of filter taps and block size. For spectral analysis, it influences the resolution and accuracy of your power spectrum estimates. In real-time systems, the buffer size impacts how quickly your system responds and how much data it can handle at once. To sum up, the best way to size buffers for large digital signal processing datasets is to match the buffer size to your signal's characteristics and your processing needs. Keep in mind your hardware's memory limits and aim for a balance between latency and computational load. Using circular buffers and frame-based processing helps manage large datasets efficiently. Combining theoretical calculations with real-world testing ensures your system runs smoothly and reliably.